This video will focus on the math behind projectile motion. We're going to start off with the equations that are used in projectile motion. In class, you learned that the acceleration in the x direction is equal to 0, and the acceleration in the y direction is equal to negative 9.8 meters per second squared, or g. We've also used these four equations before. The only difference is that now I put vector symbols on top of each variable that represents a vector. We use these with one-dimensional motion, but they also apply with two-dimensional motion, specifically with projectile motion here. The way that we will use these is we're going to look at each of these equations in both the x and the y directions. Starting out with the x direction. Again, the acceleration in the x direction is equal to 0. So if I look at this first equation, that final term, the a times t, that equals 0. So the first equation simply tells me that v final in the x direction equals v initial in the x direction, which isn't anything more than saying that the acceleration in the x direction is equal to 0. So that's not a new equation. I'm going to skip over the second equation and look down to the third equation. That one says that delta x, the displacement in the x direction, is equal to the velocity in the x direction times time plus 0, because that a is 0. Well, this equation isn't anything new. If I rewrite it as velocity is displacement divided by time, that's an equation we've already used. Looking at the fourth equation, that equation once again tells us that v final equals v initial, because that last term is 0, so that tells us nothing new. And looking at the second equation, the one I skipped, the second equation would simplify to this as well. So there's only one equation that we use for the x direction, and that is it. I've gotten rid of any initial or final because the initial is the final is the same thing as it always is in the x direction. Let's look at the y direction next. The y direction is a little different because we know that it doesn't have an acceleration equal to 0. So for the y direction, we will have four equations, and the only difference will be that we add a y subscript to everything with a vector symbol. For the delta x, or the displacement, we'll say delta y instead of delta x. So we have four equations for the y direction and one equation for the x direction. Next, we'll look at an example problem that will help us use these equations and understand how to use them. In this problem, we have a cat chasing a mouse. Classical Tom and Jerry episode. Tom chases Jerry, the mouse, across a 1-meter high table. Jerry steps out of the way, and Tom slides off the table and strikes the floor 2.2 meters from the edge of the table. It's asking what was Tom's speed as he slid off the table. Well, the first thing that you need to do when you come across a horizontal or a projectile motion problem is to ask yourself if it's horizontal or angled launch. This would be an example of a horizontal launch because Tom is going horizontally off the table. He's not getting launched at some angle off the table because it's a flat table. Because I know that it's a horizontal launch, there's a couple of things that I know without even having to read the problem. I know VIY equals 0. The initial velocity is only in the x direction. Because it's a projectile motion problem, the acceleration in the y direction is negative 9.8 meters per second squared. I'm also told that the table was 1 meter high. So Tom's y displacement is negative 1 meter. The negative sign is important because he's going downward. I also am given that the x displacement is 2.2 meters. All of these units match, which is a good thing. The thing that I'm looking for is the x velocity. Well, I only have one equation in the x direction. The one equation I have says that the velocity in the x direction equals the x displacement divided by time. But we don't have time, so I can't use that equation yet. Instead, I'll look at the information that I know in the y direction and pick an equation for the y direction to find time. The variable that I'm missing is the final velocity in the y direction. So I want to pick the equation that doesn't have final velocity, which is the one that says delta y equals VIYT plus 1/2 AY t squared. A lot of people shy away from this equation for finding time, but there are many times that you don't have to do a quadratic, and this is one of them. The reason I don't have to use the quadratic equation here is because VIY is 0. So this whole term is 0. Next, I'll solve for time. And the first thing that I will do is divide both sides by 1/2 AY. I'm going to rationalize that denominator, or get rid of that 1/2 in the denominator there. So I'll have 2 delta y divided by AY. And that's equal to t squared. To get t all by itself, I take the square root of both sides. So that t is equal to the square root of 2 times the delta y, which is -1 meter, divided by -9.8 meters per second squared. Just as with one-dimensional motion, if you end up with a negative under the radical, that tells you you've done something wrong. Go back and make sure you didn't miss a negative sign somewhere. Plugging that into my calculator gives me a time of 0.45 seconds. Now that I have the time, I can calculate what I'm really looking for, which is the velocity. Delta x, I know, is 2.2 meters. Time is 0.45 seconds. I divide 2.2 by 0.45, and I get 4.9 meters per second. That's pretty reasonable for a speed that he was going as he slid off the table. And because it just says speed, I don't have to worry about direction. So that is my final answer. Let's try one more, just so that we get a little more comfortable with these equations. In this problem, we have an Alaskan rescue plane dropping a package. The plane travels horizontally at 30 meters per second at a height of 200 meters above the ground. And we're looking for two things this time: what horizontal distance the package travels and the final velocity. Let's focus on writing down what we know first. For starters, it tells us the plane is traveling horizontally at 30 meters per second. Well, that package started off inside the plane, so that package is also traveling horizontally at 30 meters per second. It says the plane is at a height of 200 meters above the ground, so that the amount of distance that the package falls is 200 meters, but because it's going downward, we put it as a negative 200 meters. Because it says that the plane is traveling horizontally, and that package was inside the plane to start off with, this is once again a horizontal launch problem. That means that VIY is equal to 0. I also always know that the acceleration in the y direction is negative 9.8 meters per second squared. That's all the information I'm given. All my units match, so let's take a look at what I'm looking for. Part A, what horizontal distance does the package travel? Okay, so in part A, I'm looking for delta x. Once again, we only have one equation in the x direction. That equation is that Vx equals delta x divided by time, but I don't know anything about time. So just as in the previous problem, I need to calculate time. Pause the video and go ahead and do that right now. Again, we would use the equation delta y equals VIYT plus 1/2 AYT squared. And following the steps from the previous video, that means that time is the square root of 2 delta y divided by AY. Plugging in the numbers from this problem, I get a much bigger time than I did before. 6.4 seconds this time. I'll plug that time into the equation over here, but I'm first going to solve for delta x. Delta x is equal to Vx times time. My velocity was 30 meters per second. And my time is 6.4 seconds. That gives me a delta x of 192 meters. Pretty reasonable when we're talking about something dropping 200 meters. Part B of this problem wants to know the final velocity of our package. This is a question that a lot of people get wrong. So I want you to make a note to yourself that this is really important, what I'm about to say. The final velocity of an object in projectile motion is not only in the y direction. Now we're talking about the velocity just before it hits the ground, just like we did with free fall. We know that the x velocity doesn't change. In this problem, it's equal to 30 meters per second. But we know that it will also have a component that's in the y direction. So this final velocity has two components. And once we find both of those components, we'll have to find the resultant of those two components. Let's start by finding v final in the y direction. Because I know so much about this problem, there are many equations that I could choose to find this, but we might as well go with the easiest one. The one that says that the final velocity is equal to the initial velocity plus the acceleration times time. That initial velocity is 0, acceleration is negative 9.8 meters per second squared, and we calculated the time to be 6.4 seconds. (9.8 times 6.4) gives me a negative 62.7 meters per second. Negative just because it's going downward. Just as we did when we were learning just about vectors, I'm now going to draw these two components. I'm going to assume that the x velocity is to the right, even though the problem doesn't tell me anything about that. And remember that we want to put these two tip to tail. So there's my x velocity, and here's my y velocity, 62.7 meters per second. That means that the total velocity, the resultant of these two, is that blue vector right there. To find its magnitude, we use the Pythagorean theorem. And then we'll also find the direction of it. Because the problem specifically asks to find the velocity, which we know is a vector, and so it needs direction. Remember, when we're finding direction of a vector, we put an xy axis at the tail of that vector, and then we'll find the angle that that vector makes with that xy axis. So that's the angle that we'll be looking for. Go ahead and find the value of that. Find both the magnitude and direction, pause the video, and then restart it once you have it to make sure you did it correctly. You should have gotten that the final velocity is equal to 69.5 meters per second. at an angle of 64.4 degrees, and that is south of east, or below the positive x-axis. In class, we will do more example problems like this, and we'll also learn more about angled launch problems. Remember, if you have any questions about this video, to bring those questions to class with you when we meet next.